Uh, good good evening to all of you present here, and for like UK, it's like good morning to all of you. So today we have gathered here for another lecture of Geo-ORBIT lecture series. It will be the lecture 3 of the Geo-ORBIT lecture series, and today we have Professor Hing-Ho Tsang, who is a professor at University of Dundee, United Kingdom, who will be delivering a lecture on the topic geotechnical seismic isolation. So I'll hand over the session to Puran, who will be handling the entire session. Puran.
Thank you, sir, for giving opportunity to host this session. Hello, everyone. My name is Puran. I am a member of IGS Student Chapter Roorkee. I also welcome to extend my warm welcome to Professor Tsang, and I would like to call Professor Akanksha Tyagi ma'am to give brief introduction about the speaker and about the IGS Student Chapter. Professor Akanksha Tyagi, please.
Okay, so I'm very glad today that Professor Hing-Ho Tsang has joined us. To start with, he is a professor at the University of Dundee with over 20 years of international academic experience across Australia, Hong Kong, and United Kingdom. He is a chartered professional engineer and has contributed to the development of the design guidelines and standards through advisory roles to the government and industry. He is recognized among the world's top 1% of scientists for career-long impact in civil engineering, Elsevier, Stanford University. He serves on the editorial boards of several journals, including Soil Dynamics and Earthquake Engineering, which is a well-reputed journal, and chairs the global network for the GSI. Professor Hing-Ho Tsang, I welcome you today to the event of Geo-ORBIT lecture series, which is being organized by IGS Roorkee Student Local Chapter. And our student local chapter is a very active chapter, which basically organizes these kind of offline as well as online lecture series, majorly for the researchers who are, having similar interests. I'm very glad that you joined today. And over to you, Puran.
Thank you, ma'am. Thank you for the brief introduction about the speaker. Now I would like to call Professor Samadhya sir to speak a word about the IGS Roorkee chapter. Professor Samadhya sir.
No, sir, you are not audible. I think there's some problem.
Sir is not audible.
Okay. So
okay.
I think we can
move on the presentation now?
Yeah.
Sir, I kindly request you share your screen and move on the lectures. Professor sir.
Yes, I'm sharing my screen now.
Yes.
Okay, so can you see my screen?
Yes, sir.
Yeah. Yes, sir.
Okay, that's good. Let me drop the presenter mode. Okay.
Yeah.
Thank you very much for the very kind introduction. And of course, first of all, I'd like to also thank you for inviting me to give this seminar. I thank all the organizers, especially Pratik, who invited me to give this presentation to the audience in the Indian Geotechnical Society Student Chapter Roorkee, and also the staff and students in the Department of Civil Engineering of the IIT Roorkee campus, as well as other departments like the Department of Earthquake Engineering. So it is definitely my honor to give this presentation, share my knowledge with this reputable group of earthquake engineering researcher, geotechnical engineer in the world. So the topic that I'm going to present today is geotechnical seismic isolation. I think it is probably not a topic that everyone is familiar with, and that's why in this seminar I'm going to give you a brief introduction and including what I myself, my research group, and also other researchers have done in this area. And I understand that in the audience, there are mainly geotechnical engineers, but there might also be structural engineers or just general civil engineers who might not know a lot about seismic design. That's why I would like to start my presentation by talking about the design objective or the performance objective of seismic design. So this is usually the first lecture that I give in my subject of earthquake engineering. Because before talking about how to detail a concrete structures or how to design a foundation, what we need to know is what is actually the goal. So what is the goal of our seismic design? And of course, for designing a building, for seismic design of building, we know that life protection is the most important goal. And somehow this is very readily achievable nowadays with our collective wisdom and technology and experience. And so in the last 2 decades or so, more and more focus has been put on reducing structural damages in an earthquake. And that is what we nowadays call resilient design, right? Resilient structures, resilient infrastructure. And also, in order to reduce the economic impact or the impact on the society, we want the structure to maintain functionality after an earthquake. So these are the common objectives of our seismic design. And so that's why we come across a lot of terms, for example, performance-based design, which are specifically look at how we can achieve different performance level at different level of ground shaking. And as I've just mentioned, if we want to reduce damage so that the structures can still perform well after an earthquake, we call those design method resilient seismic design approaches, resilient design method. And if you can try to appreciate the overall objective of seismic design, you will realize that the goal of seismic design is not about individual structural members, is mainly about the whole infrastructure system. And so these objectives or design goals are basically at system level. So this is the message that I would like to share, and also I hope everyone can have the same ground for absorbing what I'm going to share today. And then the next thing is probably this is something structural designers are familiar with. But in case some geotechnical engineers might not know much about the evolution of seismic design of structures, then this can be a very brief introduction of what has been happening in the structural design perspective. And that is mainly when we talk about seismic design half a century ago, before the 1970s especially, we were always talking about designing higher strength of the members. Or if existing structural members are considered vulnerable, are considered weaker, then we strengthen them. So strength is the #1 important design criterion when we talk about seismic design half a century ago. But then starting from the 1970s, people or researchers are more aware of the importance of talking about the deformability of our structural members. And of course, that it comes together with the ductility of the structural members. But at the end of the day, it's about how deformable our structural members are. And apart from deformability of individual members, we also look at the flexibility of the whole structural system at the global level. And so from here, we can see that the design is gradually moving from strength to deformability and flexibility, and at the same time also moving from members level design to structural global system level design. And so later on, we also have more increasingly popular technology that is the base isolation, and also using dampers like energy dissipation devices. And so we are actually moving from member and system level, and we aim to control seismic response rather than just resisting seismic actions. And so the next question is, if we know that we are actually aiming to fulfill certain system level perspective, then as structural engineer, for example, if we are asked as a structural engineers are asked to design building structures like this, frame structures, what a structural engineer would do is to treat the ground as a boundary condition, which is kind of the basic case, especially if the ground is rigid enough to be treated as a fixed ground, right? Fixed support. Then the design would be very simple. And what they do is to detail all the structural members, sizing and detailing, right? And of course, some better structural engineers would consider the uncertainties of the ground, whether there may be soft soil, there might be uneven, unequal settlement across the whole foundation, right? And for a structural seismic designer, they know that we have to take into account the soil conditions and to quantify the site effects on the seismic loading. So this is usually where structural engineers stop in a seismic design. But we know that there are a lot of things underground, right? And of course, in this audience, most of you are geotechnical engineers. This is not something strange to you, right? You know that there could be basement structure. So should basement be considered as a structure or as a foundation structure? That is the that should be I mean the design should be carried out by geotechnical engineer or structural engineer. And what about the rock foundation? Usually rock foundation is made of concrete with steel reinforcement, right? So the design can be done by structural engineers, but it can also be done by geotechnical engineers. So the question is, should we have such a clear boundary between structural and geotechnical engineering? And what about the subsoil that is surrounding the basement or surrounding the rock foundation? Should we actually consider all these components together as the whole system in our design? I'm sure that in the audience, there are experts in soil structure interaction, and this is exactly what I'm talking about. So instead of treating the structures and soil separately or geotechnical structures separately, we should actually properly consider the interaction between soil, foundation, and structure. And usually when we talk about soil foundation structure interaction, we are talking about what is the effect of this interaction and what is the behavior of it. We seldom talk about whether we can change it, whether we can make good use of this interaction to exploit the beneficial effect of it. And this is the topic that I'm going to talk about today. Instead of just treating soil structure interaction as a behavior or as a passive mechanism, we deliberately use it as a design mechanism because this has been a missed opportunity. And so this is the kind of a new perspective that I'm going to share with you today, that is to treat the ground as part of the seismic design solution. We deliberately design the soil foundation system. We exploit the soil structure interaction, both inertial and kinematic soil structure interaction as design mechanisms. And this can be a new seismic design philosophy that I actually introduced the term geotechnical seismic isolation in 2009 in the book chapter. And I divide it as a category of seismic isolation techniques that are in direct contact with geomaterials, and of which the isolation mechanism primarily involved geotechnics. And in the past 16 years or so, I myself, my research group, and also a lot of researchers around the world have done a lot of work surrounding this theme. Some of them has explicitly used the term geotechnical seismic isolation and some haven't. But we can see that there have been an increasing amount of research which are thinking along the same direction. And so I have synthesized all these ideas, a lot of different methods and approaches, and created a comprehensive framework for understanding different type of geotechnical approaches and also categorizing them into 4 branches that I'm going to introduce to all of you today. So so this article is actually have an open access, so you can easily access this article after this seminar. So what I would like to do is to first of all introduce briefly these 4 branches of GSI systems, and then under each of these systems, I would also share with you our research finding and also the research that is conducted by different researchers around the world. So for the first branch, which is about lowering the foundation stiffness, softening the soil or softening or make the foundation slab more flexible so that it can lengthen the fundamental lateral period of the whole system. when I talk about system, it is the soil structure, foundation structure system. And so by lengthening the fundamental lateral period, most of the cases, especially when we are talking about a relatively longer lateral period of 0.3 seconds or longer, then we would expect a significant decrease in the structural demand. And then for the second branch of GSI system, we are talking about introducing sliding or rolling interface so that it can limit the seismic energy that is transmitted onto the structures. So that is basically decoupling the structures from the ground. And then in the third branch, we are talking about more like kinematic soil structure interaction. We modify the seismic wave, and of course, at the same time, if the materials surrounding the foundations have a high damping property, we can also dissipate more energy. And then for the fourth branch, which is something that you might be more familiar with, is the so-called rocking foundation or rocking isolation system that quite many other researchers have been studying. And so that is due to a series of conversation with those key players in the field of rocking foundations, including Professor Yanis and Anastasiopoulos. And so we talk about incorporating this rocking foundation into this GSI framework so that the whole system will become more comprehensive. And as you know, rocking foundation is about under designing the foundation system so that they control where failure would occur. Usually it would occur at the tip, at the edge of the foundation. The soil surrounding the edge of the foundation would fail so that it facilitates rocking and uplifting. And in some cases, it would allow sliding behavior as well. So these are the four branches of GSI system. And because I assume many of you are more familiar with the fourth branch about rocking foundations, so my presentation will focus mainly on the first, second, and the third branch. And before sharing with you our research findings and different research activities that were happening around the world, I would like to share with you something really interesting. That is kind of an analogy or a comparison with existing structural seismic design approaches. I'm sure every one of you know about the use of isolation bearings, especially the use of multi-layer rubber bearings between the superstructure and the foundation system. So those are between superstructure and foundation system. And so this is the very commonly used technology nowadays. And so for GSI, we are talking about introducing these low stiffness or soft materials between the foundation and the surrounding soil. So we move this even closer to the ground, which is fundamentally different from the structural design approach. So this is a clear analogy between the two, or a parallel between the geotechnical and the structural approach. And then the second one is actually similar. I'm sure many of you have seen sliding bearings that is also installed between the superstructure and the foundation system. And you can also see that the second branch of GSI system operates in a similar way by introducing a sliding or rolling interface. And then the third one is about modifying the ground, right? And in structural design approach, we modify the structural dynamic properties by introducing dampers or energy dissipation devices. So it's not exactly, but kind of in a similar way, because it also modifying the behavior of the structural system. And in our case, in GSI, we modifying the ground by modifying the modifying the seismic wave propagation by modifying the ground properties. And also, both of them can also dissipate energy through hysteretic damping, for example. And in the fourth branch, that is probably more of you will be familiar with, is actually analogous with the capacity design principle in structures. For structural design, we deliberately select locations where we want to see the failure mechanism to occur, and that is to introduce the use of plastic hinges by different type of special detailings in those at the end of the beams, for example. And in the fourth branch of GSI system, we deliberately design failure at the edge of the foundation system, and so that there will be soil failure. So the concept is actually similar, and that's why we can see that for all 4 branches of GSI system, there are parallels with the structural design approaches. Those are actually 4 major structural seismic design approaches that we are using nowadays. And so we have quite a comprehensive framework that integrates both geotechnical and structural seismic design methods. And so to summarize what I've just mentioned, GSI, Geotechnical Seismic Isolation System, is a new design philosophy that extends seismic design into the ground, into the geotechnical domain, so that in the past, we are talking about, as for geotechnical and earthquake engineer, we are mainly studying the dynamic properties of soil, we are studying the behavior of liquid fraction. And so GSI actually try to also expand geotechnical earthquake engineering so that geotechnical engineers can play a more significant role in seismic design. And to do this, we engineer the soil foundation system or engineer the interaction of the soil structure interaction with ground motion in order to reduce seismic demand. And it's actually a kind of quite a multidisciplinary discipline or multidisciplinary field of study that integrates soil dynamics, of course, foundation engineering, and also the seismic isolation principles. And of course, it also involves a lot about material properties, materials engineering. And all these can be operated under a unified framework that is based on mechanism. And so what I will do is to introduce a series of different studies conducted by many different people. And because of the broad background of people in the audience, I would not include theoretical stuff or equations. I want everyone to be able to follow every single slide and just mainly to look at the possibilities of GSI and what kind of research we can do to advance GSI as a branch in earthquake engineering. So under the first branch, which is also the most commonly researched branch of GSI system, that is based on modifying the foundation soil to make it like a more flexible base or flexible foundation. So my research group has done a series of centrifugal testing and also 1G shaking table tests. So for example, we have do it for example, the subject structure can be a building frame, or it can even be some energy infrastructures like a transformer structures that we can see on the right-hand side of this slide. So for example, we did centrifugal testing based on the use of gravel rubber mixtures, which is the most commonly research materials for GSI system. So we did 50G centrifugal testing, and this slide tries to summarize the ultimate effect of the system. That is, the structural demand can be reduced by, on average, 40 to 50%. And at the same time, I'd like to also bring to you the attention of the amplification of foundation response. And that might be seen as something not favorable, but if you look at the extent of amplification of the foundation displacement and the absolute amount of displacement, they are actually not excessive. They are definitely controllable. They can be easily tailored for in the design process. Both the foundation horizontal displacement and also rotation can be amplified, which are actually beneficial. It's similar to the use of base isolation bearings because the whole building actually also move quite significantly, but the structural demand, the interstory drift, and the deformation of structures can be significantly reduced. So the mechanism and the effect is actually similar. Apart from gravel rubber mixtures, we also explore the use of other materials. Rubber materials might not be very well accepted in some parts of the world for foundation engineering, right? But as we all know, as geotechnical engineers, we know that EPS is a very commonly used, well accepted materials. Material properties is more well known. We can use the whole piece of EPS block that some of my research projects dealing with at the moment, but I have also done centrifugal testing with the use of EPS bead sand mixture. And so in this case, we can also reduce the modulus of the foundation soil. As you can see, we on this slide, we can see that the on the right-hand side, we can see that the rocking stiffness has been significantly reduced by close to almost 10 times compared to lateral soil, like in this case is sand. And then we can also see a further reduction of the rocking stiffness when the shaking level is higher. So this is an advantage because when we are talking about stronger earthquake shaking, we would expect larger foundation rotation. And because of the further reduction of the rocking stiffness, structural demand can be further reduced, which is actually a benefit of it. And then we can also see the hysteretic loop of the base moment against foundation rotation, and we can clearly see that base moment can be significantly reduced if there's just pure sand or other type of lateral soil. We would expect that there might be certain uplifting in the foundation, which in some cases is beneficial, but there are also disadvantages, right? So with the use of GSI with softer materials in the ground, we would expect that the rocking rotation can be increased, similar to the case when we have just rocking foundation, the fourth branch of GSI system. But at the same time, there will not be uplifting. They can actually minimize a lot of damages or a lot of undesirable effects that might happen, right? And at the same time, we can also look at material properties. We can look at the hysteretic loop, showing larger hysteretic loop. That means there will be higher level of damping. And I have also explored the use of the so-called high damping polyurethane. And it is actually a trademarked material called Tsang, but there are actually different type of high damping polyurethane that we can explore. And we can see from the hysteretic loop that there is the wider hysteretic loop. That means there is higher energy dissipation. And I have tried to explore 3 different configurations of GSI system. On the left-hand side, we have the high damping polyurethane surrounding the entire foundation. And for the middle case, we just put the materials at the peripheral of the foundation so that it can be used for retrofitting existing structures more easily. And in the third case, we have the material just underneath the foundation and leave the periphery untouched. That means they are disconnected. And there's a so-called lateral disconnection that some researchers like to name it. So we can see that very significant reduction of seismic demand can be observed if we are looking at the material surrounding the entire foundation. A reduction of an average of 60% can be achieved. Even if we just put it at the peripheral, we can expect on average 35% reduction in structural demand. And if we even leave a gap, that means the lateral disconnection technique, it can even reduce structural demand more significantly by an average of 65%. So this is a very significant achievement. And so I would also like to, as I mentioned, like to share with you the research that were conducted by other researchers. For example, from the right upper corner, we can see a consortium of researchers in Chile and also from MIT, Professor Eduardo Causo, who have proposed a lot of soil structure interaction model and how to model nonlinear properties of soil. And he has applied his model for modeling this GSI system in such a simple manner. And they have achieved a fantastic reduction outcome as well. And then there is a very strong geotechnical earthquake engineering group in Thessaloniki in Greece. They have done numerical studies and also field testing in the almost full-scale field testing facilities. And they have also measured the reduction in structural demand. So that means the effectiveness of GSI system, especially in this case based on rubber soil mixtures, has already been proven successful through numerical, analytical, centrifugal testing, field testing, and shaking table testing. So almost all kinds of testing have been done to prove the effectiveness of such a system. And then apart from the use of rubber soil mixtures, there have also been other materials that were explored apart from what I have done before, as I've just shown you. some researchers in Japan have introduced the use of nylon fibers into the rubber soil mixtures as an additional improvement of the materials. And then pure rubber were used in this case for bridge pile column, bridge pile foundation. And then Professor George Melonakis in Bristol has also explored the use of EPS foam for retrofitting existing bridge piers. And then there is also a consortium between Naples in Italy and Cambridge in the UK who study lateral disconnection. They try to soften the foundation by removing materials without replacing by other type of materials to look at kind of a more extreme conditions when there's no material surrounding the foundation system. So in this case, of course, they also observe very positive results, very significant reduction of structural demand. And they have also measured the settlement, which is slightly larger than the case when there is no lateral disconnection. And they have also measured the rotational stiffness or rocking stiffness, which show a significant reduction. And they have also measured the moment rotation hysteretic behavior. And then another group led by John McCarthy in UC San Diego, they have done full-scale shaking table tests. They have, of course, measured a lot of things, have done a series of different testing, but the most interesting result, in my opinion, is the self-centering capability, because this is something some people might concern when we talk about the use of soft materials in a GSI system. In this case, in their test done by Professor McCarthy, they have actually used 100% rubber. So that is the softest possible case when we are talking about the use of recycled rubber. So supposedly we have the greatest concern with such a material, especially about settlement and also bearing capacity and also self-centering properties, right? In their test, in their full-scale shaking table test for having a footing surrounded by tire-derived aggregate, they, of course, they observe some settlement, which might be quite marginal. So you can imagine that if 100% rubber might give us marginal settlement problem, that means if we use lower rubber content, then it should not be a problem anymore, right? But more importantly, what we can see is on the horizontal axis, we are actually showing the sliding and the rocking of the foundation. And the square symbols is showing the initial location, of course, that is 0. And then the residual would be after shaking, right? After shaking, we actually do not observe significant or even just minimal sliding and rocking. So this is very encouraging and very promising to see such a result. And then there is another group in another part of the world, in University of Canterbury in New Zealand. They have got a huge funding because they see a lot of potential in this technology of GSI. They got a lot of funding from the industry and also supported by the Ministry of Business, Innovation and Employment. They have done a lot of testing at material and system level. And apart from just replacing the foundation soil, they also want to introduce rubber and also steel fiber to make concrete. So that means steel fiber reinforced rubberized concrete foundation system. And so this is, I mean, in addition to softening the foundation soil, they also soften the foundation, the structural foundation system, so that it can make the system even more flexible to lengthen the fundamental lateral period more significantly. So this is a very good extension of GSI research, and their work were actually awarded the Outstanding Paper Award by the International Association for Bridge and Structural Engineering. So apart from studying at the system level, of course, there have been a lot of research that is about the material properties. In particular, the most researched material for GSI system is rubber soil mixtures. Different type of rubber, different size of rubber, and also different type and size of soil particles. And significantly, the Thessaloniki group was one of the first group who picked up this research after I published my first paper in this area in 2007 and 2008. They have done a series of comprehensive static and also dynamic testing on the material properties. They try to develop an analytical model to quantify the material properties and also for input into analytical and numerical studies. And there are also research groups who have been looking at the micromechanics of such a four-phase materials involving a deformable phase. And then we have also tried to improve the material properties of proper soil mixtures by introducing different materials like polyurethane and bitumen. And then apart from the commonly researched material of rubber, there are also research on the use of super absorbent polymers. And this Italian group in Naples, they have actually commercialized their technologies based on the use of super absorbent polymers. And then the group in Turkey have explored the use of EPS beads and also geofoam as well. And then the group in Japan has worked on nylon fiber to improve the ductility of the mixture. And I'm sure that up to now, a lot of smart geotechnical engineers would have a question on your mind, that is, would there be concern about settlement, both at the static condition after building the structures and also during an earthquake? So the good news is they are not excessive. The settlements are actually not excessive. So if we are talking about the static case, or in this table, we summarize the results. With the use of EPS bead sands mixture or the high damping polyurethane materials, we measure the static settlement or the immediate settlement after having the full weight of the building. So we are talking about 10 to 15 millimeters of settlement. And the good news is that they are uniformly distributed. And so there's no uneven settlement. And even the absolute total settlement is actually not significant. The most stringent design guide gave us a limit of 25 millimeters, and still there is still quite a wide margin. And I'm sure that a lot of design guidelines and codes of practice are talking about 50 millimeters of limit. And so we are far lower than that limit. And then during earthquake, an interesting result is that because of the deformability of the materials, and most of the deformation has already occurred during static case, right? And so during an earthquake, there were just an additional of 3 to 6 millimeters of settlement, which is even smaller than the settlement that is induced by earthquake shaking when we have lateral soil. It can be gravel, it can be sand. So the average settlement would be in the order of 10 millimeters for pure sand or pure gravel. Okay, and so with the use of GSI system, the settlement can actually be reduced. So we measure this in centrifugal testing. And then for rubber soil mixtures, I try to do analytical calculation and also numerical simulation. And we find that if we use rubber soil mixtures of thickness 2 meters or less, even up to number of story of 8, ground settlement will be smaller than 10 millimeters. Static ground settlement. So this is definitely not excessive, and they are evenly distributed. And if there is still any concern about excessive settlement, probably your friends in IIT Madras, they have done research also with the use of sand rubber mixtures, and they have tried to introduce the use of GeoGrid to reduce settlement even further. So even before having GeoGrid, the settlement is just 2.5 millimeters in their studies during shaking. So it's earthquake-induced settlement. And then with the introduction of GeoGrid, they can reduce the settlement to just 1.2 millimeters. And in your neighboring country, in Nepal, they have already introduced this technology to the industry, to the community after the 2016 earthquakes. And they have also adopted it in some pilot housing and pilot facilities. And so this is just an example that they share with me. Okay, so I have probably talked a lot about the first branch of GSI system, and that is because those are the most researched and of course, there are many more other researches done by other researchers. So from here, I'd like to talk about the second branch of GSI system, and that is based on a sliding base. And a very significant study that was conducted quite a while ago, more than 2 decades ago, were conducted by Professor Yakian in Northeastern University in Boston. So he and his colleagues have introduced the so-called foundation isolation or soil isolation, which are now part of the GSI system. They try to experimenting the use of smooth geosynthetic liner like geomembrane to allow sliding between the foundation and soil, or between different soil layers, like the one on the right-hand side. And this concept has also been further explored with the use of different materials like PVC or sand or roller bearings. And these were explored by researchers in mainly in Bristol, and also in collaboration with some researchers in ETH Zurich. And then also another group of researchers in Croatia. They have done very interesting research by exploring the use of different materials like stone pebbles, limestone sand, different type of geosynthetics. And their work, I mean, is mainly done by a former PhD student, Ivan Banovic. His PhD thesis have got the best PhD thesis award from IABSE. And then there are also hybrid isolation system involving both geotechnical seismic isolation and structural type of isolation, and that is targeting rural brick masonry house model. And so we can see that the use of gravel pad underneath the foundation is a geotechnical approach. And then there is also a sliding layer at the ground level between the brick walls and the foundation structure. Okay, and then in the third branch of GSI system, there could be a lot of varieties that we can imagine, because there are less limitations. You can do whatever to the ground as long as it is practical and it can reduce ground shaking or reduce structural demand. For example, in the paper published in 2009 by the Thessaloniki group, they have considered different stiffening approaches and also different softening approaches. The three at the bottom are softening approaches. They are different from the first branch because we would expect much less interaction between the filtering layer. So this soft material there in diagram D is a few meters away from the foundation. And so there will not be much inertial soil structure interaction as we can see in the first branch. But at the same time, this is more like a filtering layer to filter the seismic isolate seismic wave, or it actually reflects seismic waves. And then there are trenches. Trenches are typical for filtering as well. And this is what they call a caisson. A caisson is also more for filtering seismic waves. And so this can be considered the third branch of GSI system. And then later on, a group in Naples and also in Cambridge have taken this idea further and then did centrifugal testing to observe the results. And then there are also different approaches and different type of testing that were done, for example, by a group in Japan and also in collaboration with a researcher in Auckland. And they have measured the change in acceleration, maximum acceleration in the simple, and they actually did pseudodynamic testing. So that means they have done both experimental and numerical simulation at the same time, looking at the maximum acceleration and also pore water pressure ratio. That is to look at the liquefaction potential and the use of rubber, pure rubber, and also rubber soil mixtures. They find that they can significantly reduce both maximum acceleration and pore water pressure. And more recently, we have looked at the use of a filtering layer to look at the use of rubber soil mixtures, not for the first branch, but for the third branch. We observed the filtering effects. And then we also look at the reduction of excess pore water pressure ratio and also the liquefaction induced ground settlement. So we just published a paper very recently on these new results based on OpenSea's modeling that I believe many of you are familiar with. And then there are also some other interesting academic industry collaboration. This work is quite significant as it's supported by a major chemical company, master builders, and of course they also supply materials for ground improvement and so on. In Italy, they have tried to explore the possible use for retrofitting existing heritage structure, for example, a cathedral like this. They try to drill holes through the foundation system so that it is less intrusive, less invasive, and they try to inject polyurethane foam. Those are expandable polyurethane foam, so that there will be a series of polyurethane foam columns underneath the foundation in order to create a GSI third branch system to filter or to scatter seismic waves. And then there are also research about the use of trenches. It can be unfilled or filled by EPS geofoam or filled by rubber soil mixtures. And there are also another group of researchers who are doing research on the use of metamaterials or periodic foundation. So these can also be considered GSI system of the third branch. So these are the street of different research activities and also some of the applications that people have been exploring throughout the past 2 decades or so. So in a nutshell, in one-page summary, we are talking about a conceptual framework of GSI system that are categorized based on their governing isolation mechanisms. And in fact, the isolation mechanisms of these 4 branches of systems are not mutually exclusive. Some of them can actually work together in synergy so as to improve the isolation effect to further reduce structural demand. And this paper has open access, right? And so I would encourage that everyone can have a look of this paper. And I can observe that this is going to be even increasingly popular because I'm in the editorial board of Soil Dynamics and Earthquake Engineering, and I just received a report from the publisher. And one of the slides is showing the most downloadable paper amongst papers published in 2025. That means the year this paper is published. And this paper was the second most downloaded paper since it was published. And so I'm sure that it is going to be even more popular, and it is going to change practice, hopefully. So apart from this state-of-the-art paper, we have also published a special issue collecting a lot of advances of GSI system. In this special issue published in the Bulletin of Earthquake Engineering just 3 years ago. And then there's an ongoing special issue on geotechnical seismic isolation in the Geosynthetics International Journal. So this is a very, very good journal of geosynthetics. I'm sure everyone know it. And what is important, the important message that is I would like to share with you is that it's not only about earthquake engineering, it's also about the use of synthetic materials in civil engineering. So, and it's also expanding the use of geosynthetics for earthquake applications, especially for base isolation. And so for this purpose, for this special issue, I was also invited to write an overview paper of the possible materials that can be used for GSI. So many of those are synthetic materials. And obviously, up to now, I'm sure that you know that rubber, recycled rubber, is one of the key materials that we can explore. And that's why there have been a lot of research about the use of that recycled rubber in different formats. And I have also tried to synthesize different researches that were conducted in the past 2 decades in this along this direction. And I tried to also group them into 3 other groups. Apart from recycled rubber, there are 3 other groups. The first one is geofoam. Either use it in a block form or use it in beads mixed with sand or other type of soil. And then the third group of materials would be planar geosynthetics, like geogrid, geomembrane, geotextile, this kind of planar geosynthetic material. And then the fourth group of materials, synthetic materials, is what I call functional polymeric materials. And these actually open up a lot of opportunities for material innovation, right? Because, for example, we can see there are three different types of functional polymeric materials. On the left-hand side, this column is showing the expandable polyurethane foam. And in the middle one is the high damping polyurethane. The right-hand side is the super absorbent polymer. And there could be many other polymeric material that we can tailor design to make it functional so that it can serve the purpose of GSI, either by softening the foundation soil or by enhancing damping or any other advantages that you can think of. And there are also some other activities that has been happening. For example, the special section of GSI in the 17th European Conference on Earthquake Engineering. And then there was also a technical section on GSI in the World Conference. And we had about 30 papers in this section that, our section was actually broken down into 3 sections of a total of 5 hours. So you can see a significant momentum direction. And we actually also had a regular, a special section in the conference in Zurich 2 weeks ago, the International Conference on Physical Modeling in Geotechnics. So there are also a lot of interesting papers presented in that section. And a few years ago, some of us, including many researchers in Europe, were very interested in gathering together during COVID time, especially at that time. And it started from a very small group when people like to just interact and try to share knowledge. And then it has since then been growing to a more significant, larger group. And I'm sure that you are able to see some of your friends from different countries, different institutions around the world. And of course, because the group has been growing, and I haven't updated the slide to include all the faces here. So if you are also working along this direction, you are also welcome to join us in this global network. So to summarize, not about the technical aspect, but about the objectives or the benefits of this GSI approach, that is, it actually aligns with 3 major global priorities in civil engineering or in earthquake engineering. So we are talking about in an isolation system, we are talking about low design, right? Because it is consistent with other structural seismic isolation systems that can reduce damage. And then you can also see that we are talking about the use of low carbon materials. We are talking about the use of recycled materials, and even the use of geosynthetics. A lot of different types of geosynthetics are considered low carbon. And so it fulfills the sustainability aspect of our construction industry. And also because the GSI system can be readily used for retrofitting existing infrastructure system, and that makes our infrastructures even more sustainable. And you might also be able to see that the technology itself, because it is dealing with the soil foundation system, so it doesn't matter whether it is a frame structure or wall structures, whether it is energy infrastructures like the transformer or a wind turbine, whatever structures. The different type of GSI system can also be tailor designed for different purposes. So it can be broadly applicable to different type of structural systems, infrastructure system, and also because of the use of geosynthetics, many of those are actually cheaper, more economical, and it doesn't require advanced technologies. As you can imagine, the fabrication of bearings could be expensive and might not be accessible in some rural areas. For example, rural area in India, you might not have access to those advanced technologies, both economic-wise and also technology-wise, right? But for GSI, we are just mainly talking about changing the properties of the ground, right? And there are a lot of options that we can explore, and many of those are just like soil improvement or even just a site formation stage of a construction project. And so they can be universally applied to any kind of structures anywhere in the world. So that's why it is also an important benefit of such an approach. So that's basically the end of my presentation, and I hope you enjoy it, and I'm looking forward to further discussion.
Thank you, sir. It was a wonderful lecture. I hope everyone enjoyed and learned something. Now we can take a couple of questions from the participant that is in the chat box. So, sir, can we start about the question answer? Hello.
Should I stop sharing? Yeah, I guess so.
Sir, can we start with the question answer session?
Yeah. So please feel free to ask any questions. Should I look at the test?
It is in the chat box.
The chat box, or?
In reality, there is one question. In reality, how can we quantitatively separate the contribution of each isolation mechanism when multiple mechanisms act at a time?
So I cannot hear clearly. So you said there are multiple isolation mechanisms. How can we quantify the effectiveness?
Effect of like each isolation mechanism.
How to quantify the mechanism or quantify the effectiveness?
Let me ask the questions, Purun. The question is, in reality, how can we quantitatively separate the contribution of each isolation mechanism when multiple mechanisms act simultaneously?
Oh, okay, I see. So it's more about research, right? I suppose we have to kind of separate different isolation in the study. So it's kind of isolating one mechanism from the other in order to, so it depends on how we design the experiment. So if we can isolate one mechanism from the other, then we can study them separately, right? So it's more about the design method, research method, rather than the mechanism itself, right?
Okay. And
So for
the next
example,
question
if we
is,
talk about the filtering effect, then we can do it without considering structures so that there will not be inertial soil structure interaction, and just look at how seismic wave is dissipated or is filtered through traveling through a layer, right? That can be one way of isolating that. Yeah, so we have to look at it case by case.
Okay. And like we have witnessed many materials you have used for the geotechnical isolation. So what are like how stable are the mechanical properties of these materials? Like if we talk about 50 or 100 years, so on the basis of aging, temperature variation, moisture, and repeated earthquake loading. So how about the mechanical properties of these materials?
Okay, so in general, so I'm sure everyone knows that rubber is actually a very durable, it's an inert material, chemically inert. So rubber itself is actually very durable. So there's no doubt about that. So the problem is whether there is aging effect, right? But if you think about it, all kind of structures have aging effect. So concrete have aging effect, right? And so there have also been a lot of studies surrounding that. But the most important is if rubber itself is durable, and if it is put underground, so that means there's very minimal oxidation process, then the materials can last very long. So that is definitely beyond 50 years of design life.
Okay. So the next question is how we avoid the potential amplification of a structural response caused by coupling the natural period of the structure with softening of the surrounding GSI soil.
Yeah, so it is about how much you understand about soil structure interaction, right? So the very simple way to look at it is if we decide, we look at the spectrum, right? There is a constant acceleration and then the hyperbolic function. So we have to design the GSI system such that the lateral period is moved from kind of from a high acceleration demand zone to a low acceleration demand zone, right? So in fact, there is quite a long hyperbolic function, right? Beyond about 0.3 or 0.4 seconds, there is a general decrease in acceleration demand. So this is one thing, just about purely about period lengthening, right? And additionally, we also have the damping component, not only about the radiation damping, but also material damping. If we are using, for example, rubber or high damping polyurethane, there are two components that contribute to structural demand reduction. So that actually reduces the chance of having any amplification, right? But even if we just look at the period lengthening mechanism only, we can easily decide it based on the design spectrum, right? This is not too different from quantifying the effect of soil structure interaction.
Okay. Thank you, sir. I think
very good questions. These are all good questions.
I think we are running out of time now. So I think the more questions, if you have any query, people who have queries, they can, I think, approach Professor Hing, maybe by mail or something. So Puran, I think now we can call Devdeep to present the vote of thanks, I think. Yeah. Devdeep?
Yes, sir.
Yeah.
Good evening, everyone. On the behalf of Indian Geotechnical Society, Student Chapter Roorkee and Department of Civil Engineering, IIT Roorkee, I extend our heartfelt gratitude to Professor Hing for delivering such an insightful and informative lecture on geotechnical seismic isolation. Through your lecture, sir, we gained a clear understanding of basic principle of GSI and its growing importance in earthquake-resistant design. The concept, the method, and the practical example you are shared have improved our understanding for this emerging field and open up new ideas on how geotechnical solution can help build safer and more resilient infrastructure. We are truly grateful that, sir, you took time for your busy schedule to be with us today and share your expertise with the student, researcher, and faculty members and fellow professionals. Your work in this field is genuinely inspiring, and I'm sure it will help and encourage many of us to explore new direction in geotechnical research and practice. I would also like to thank Department of Civil Engineering, IIT Roorkee, our faculty members, all the participants who are joining us today, and dedicated members of IGS Student Chapter Roorkee, whose collective effort made this lecture possible. With that, we'll close the session today. Thank you once again, sir, Professor Tsang, and wishing everyone a pleasant evening.
Thank you very much, everyone. So it has been my honor to share my knowledge with this brilliant group of audience. Yeah, thank you very much again for the invitation.
Yeah, Professor Hing, before we leave, I think we should open once the camera so that we can have a group photo. I request everyone to open the webcam so that we can have a group photo.
So thank you, Professor Tsang. Very insightful, interesting topic and very useful topic for the students. I thoroughly enjoyed, and I also had some questions, but since we are running out of time, I cannot ask.
Yeah, please feel free to send me any questions through email, and we will definitely continue this dialogue. And yeah, I enjoyed this interaction, and yeah, so probably my presentation is longer than expected. So I'm so eager to share as much as I can. Yeah, so I didn't really look at the time when I presented. Yes, but I hope everyone enjoyed it, and we can certainly keep in touch.
It was amazing.
Yeah.
Thank you.
Thank you, Professor. So I think now we can close the session.
Oh, are we not taking picture?
Yeah, we have taken the picture, sir. Yeah, picture.
Okay, that's good.
Yeah. Sure, sir. Thank you.
Okay.
Okay, thank you very much.
Thank you.
We'll keep in touch.
Thank you,
Have a
everyone.
great weekend.
Yeah.
Bye-bye.